I'm Celine Ling from Rice University, so I will be moderating this keynote section. Next, it's my pleasure to introduce Intel Fellow Lama Nahaman. She's an Intel Fellow and the Director of Human and AI System Lab in Intel Labs. Her research focuses on creating texturally aware experience that understand users through sensing and sensing making, anticipate their needs, and act on their behalf. So at Intel, she leads a multidisciplinary team that explore new user experience, sensing systems, algorithm, and applications. So with her 23 years experience in the area, under both commercial and industry settings. So I believe her talk would be very interesting and inspiring. Lama, she's here, but because she's traveling, so she pre-record her talk. So next, I'm gonna play the video. She'll be here for the live Q&A.
Hi, my name is Lama Nachman. I lead the Human and AI Systems Research Lab in Intel Labs, and I'm very happy to be here with you today, even though it's virtual. So I will be talking about amplifying human potential with AI and how can we get human and AI to collaborate to provide better outcomes. So to start with, I'll just say a few words about my lab. So we're actually a multidisciplinary team that spans social science, design, and AI, and we take a human-centered approach. So what we try to do is essentially to go out with ethnographic research and try to understand what problems need to be solved, how can technology come into people's lives and help support people's needs. And then from there, we start to kind of dissect this into different types of experiences that are possible. Then we'll go build a lot of the capabilities in AI and sensing to try to support that. So in a high level, we're trying to really understand how technology can come in to support people in their everyday needs and lives throughout the typical experiences that people would have. So what we've been really trying to do is kind of change the narrative from a human AI competition to a human AI collaboration. So as we think through different aspects of our lives, whether it's in settings like smart homes and how do we support elderly to age gracefully in their homes, or how do we bring in sensing and AI to help support people as they perform jobs within manufacturing setting, like for example, an Intel fab, or how to support students in terms of learning and having better learning outcomes. And then also looking at areas like assistive computing, and specifically, how do we support people with disabilities with sensing and AI? So I'll talk about some of those possibilities and where do we see a lot of the potential within this space. So let me start with manufacturing, an area clearly at Intel that we do quite a bit of. So we've kind of taken that user-centered approach and went into the fabs and tried to kind of understand how can AI come in to try to support people as they perform tasks, right? So if you think about a typical manufacturing setting, you could imagine looking for areas where, okay, there's a very repetitive task. We would want people to, try to optimize the type of work that's happening. So maybe we look at a repetitive task and try to automate people out of the loop. However, if you actually think through the complete workflow in a manufacturing setting, it's really much more effective to try to think through all of these different steps within a task and think about how do we bring humans and AI together to actually improve the overall outcomes, right? How do we improve productivity? How do we support people as they perform tasks? How do we support them in learning and things like that? So we've been actually looking at these different tasks that people do within a manufacturing setting and think through the different steps within that task, and then look through how we could actually bring AI and sensing to help support people as they perform the task. So typically in these manufacturing settings, you'll see kind of very rigid multi-step processes, but those are usually described in some form of a manual or a spec or something like that. So you could actually bring the AI system to consume all of this information from the tasks. So you understand kind of all of the different sub-steps within a task. And then you can train an AI system to actually observe people's actions and perform action recognition. So now as the person is actually performing that task, you could actually understand that they're okay doing step 1 of that task, step 2 of that task, and so on. And then if you put those two things together, you could start to actually guide the user as they're performing the task. So now if you, for example, observed an experienced person doing the task, and then you have now a novice who's actually performing the task, you could actually start to give them guidance, bring information that is relevant to the specific sub-step that they're in, or if they actually perform the wrong step, for example, or out of order or something like that, then you can actually highlight that. Or if they forgot a certain tool within the piece of equipment that they were working on, then you could actually highlight that and say, hey, there's something that's actually out of order. Now, in that sense, that's the part that the AI is actually helping the human. But if you actually think about it from the other direction, we all know that AI systems are very brittle, that they don't actually quickly adjust themselves to changes in the environment. If there is actually a change in the type of tools that are being used or whatever, it's very hard for the AI system to just kind of automatically adjust to these things. However, with human guidance, right, you can actually provide feedback to the AI system that says, okay, well, now I'm actually performing this step, and this is the actual tool that we actually now are using. And over time, you can actually continue to train the AI system so that it can evolve through this collaborative process with the human. So that's actually what we kind of perceive as an interesting way of thinking about how AI can come and support humans as they perform these tasks, and how the human can actually continue to support the AI system in this continuous learning, and especially in ambiguous situations where humans tend to actually do much better than AI systems. So that's in smart manufacturing. So let me take another example and talk about education. And in education, we all know from the pedagogy research that that learning outcomes really correlate quite a bit with level of engagement that students have. So the idea becomes, like, how can an AI system then observe and understand human engagement and then help personalize that learning experience? So we can figure out human engagement from a lot of different inputs, right? You could have as the learners actually doing certain tasks on their PC, like consuming some content or doing some tests and things like that. You could actually try to observe the human from the camera that's in the laptop, for example, from the content platform and everything that they're doing with that content platform, and use both of these inputs to infer the level of student engagement. And when you think about student engagement, well, the thing that's relevant to student engagement are things like, are they satisfied? Are they bored? Are they confused about the specific task? So you could actually teach an AI model to actually observe that. Now, once you've done that, then you can use that information to help enable teachers to understand better student engagement, specifically when they're actually engaged with the PC. It's harder for the teachers to try to understand that level of engagement. You can actually bring that information back to the student to help support them and enhance their awareness. But you could also use that input in the educational platform and continue to personalize the type of tasks that the content platform is actually supporting them with. So, one of the areas, this is an area that we've been doing quite a bit of work in for many years, right? And deployed these in different schools to try to understand what type of states are important. Can we actually understand learner engagement in these settings? And if we did, can we then bring that information back to the teacher to help assist the teacher and amplify the teacher's ability to support their students? And one of the things, after we've kind of done multiple deployments to try to collect the right data and build the right models and all of that, one of the things that we did is we actually then deployed this in a real classroom environment to try to understand how effective would that be in supporting the teacher's understanding of the student engagement. And if that happens, how does that actually change the outcomes or the interventions within the classroom? And then, what we found out is actually, if you look at two classes, one that's supported with this technology and one that is not, you actually do see a very different behavior that the teacher actually exhibits in these settings, right? So in the control group, where actually the teacher was not enabled with this information, you'll see a lot of close monitoring. The teacher will walk around, try to understand as the students are engaged, with the content platform, whether the students are actually doing okay, or they're confused, or they need help. Whereas if you look at the treatment class, where the teacher is enabled with this technology, you'll see less of that close monitoring and more time that is spent in supporting the students that need help. They go directly to a student that they think are confused based on the input of the system, and then they can help them with scaffolding and supporting them better. Now, as you kind of transition, this is what we were describing in terms of, well, okay, that learning is happening through the PC, and it's that type of environment that's actually enabling that to happen. Now, if you think about with students that are much younger, younger students tend to actually learn physically, right? They're learning in the physical environment. If you go to a kinder classroom, for example, you'll see kids sitting on the ground, on the rug, playing with objects, right? Learning math by putting manipulatives together and understanding their tens and ones and so on. So one of the areas that we've been exploring is, can you actually turn that whole learning environment into a smart environment, right? Where you could see this picture of this cute teddy bear, Oscar, who's actually trying to support the kids learn in that physical space. So the kids could be, on the floor working with these tens and one objects and putting them together. And, Oscar could be giving them numbers that they're supposed to form through these different objects. And the AI system is able to actually look at that environment, have a shared understanding of what they're actually doing, recognizing the actions that they're doing, and then having a dialogue with the kids that is actually rooted in that physical environment. So now if you kind of imagine how kids actually speak, right? They're not speaking the way that we speak with an Alexa, for example. What they're actually doing is that they're pointing, they're touching, they're nodding, right? They're agreeing and disagreeing with gestures and things like that. So as you start to build a conversational system, it's not sufficient to build a conversational system that can do that just through speech. It needs to actually be able to observe the students, to actually have a dialogue with them that's rooted in that physical environment and the specific actions that they're doing, which tends to be kind of an interesting and complex way of actually building a dialogue system that's totally contextually aware, that's able to take in all of these inputs from multiple modalities and help enable that interaction. A third area that I wanted to talk about was assistive computing for people with disabilities. And that is actually probably one of the projects that I'm most proud of in all of the work that I have done. And this is actually the work that we have done with Professor Stephen Hawking to enable him to communicate by essentially turning one simple signal that he could give. And in the specific case of Professor Hawking, he was able to actually move his cheek. So if you look at this picture and you see this device right here that's actually sitting off of his glasses right by his cheek, this is actually a proximity sensor. And this proximity sensor, which really kind of acts in the same way that a proximity sensor in your phone does, right? When you bring your phone next to your ear, it actually detects that there is a difference in distance, right, from what's in front of the proximity sensor, and it starts to trigger based on that. So in the specific case of Professor Hawking, you could think of it as the equivalent of him pushing a button with his cheek. So as he moves his cheek up, it actually changes that distance to the proximity sensor, and is the equivalent of literally pushing a button with his cheek. So how does that then work? So essentially, there is this context-aware toolkit or software platform that runs on top of the PC that essentially changes all the different interaction, everything that you could do with your PC, like write text, use that text to then do text-to-speech, surf the web, write documents, send emails, things like that. We would change all of that to be controlled by this simple push button. And the way you would do that is by actually making the system very contextual, because the minute you can actually change everything to be a selection of a few things, and you can actually do the equivalent of a push button, then they can make that experience way more efficient, because all they need to do is just kind of select one of n options. So, this platform essentially then takes the context of what they're trying to do and maps that across these different things to actually map into a set of a few options that they can select from. So we took that platform and we put it out in open source so that anyone who has ALS or a similar disability can actually end up using this system. But what's interesting here in that system is that while for Professor Hawking he was able to actually move his cheek, with other people with disability, they might be able to say maybe move a finger or raise an eyebrow or move an eye to the right or to the left. So really what you want to do is be able to capture any type of movement and turn that into the equivalent of a push button. And then you have a system that can support them to essentially do anything from whatever signal that we can capture. And one area that we've been working on quite a bit recently is actually trying to turn brain-computer interface with very simple sensors and a lot of signal processing and machine learning to be able to actually extract the equivalent of that push button from brain waves. So, and that works for people who have no ability to move any muscle whatsoever. What's interesting here is that all of that interaction that we've talked about was really kind of at a lower level of interaction, right? So people put together letters and choose through word prediction specific words, and that enables them to effectively communicate. But if you think about it, you could actually elevate the level of interaction higher to be able to actually even support much faster interaction. So if you think about somebody with disability, you're imagine having a conversation with someone who's not able to speak and not able to type, right? So the person would start speaking, and once that person is done speaking, then the person who's trying to communicate will start to put together these letters and select words that are predicted, and then the system will eventually speak what they said. The problem with that is that there's a long silence gap. So what we're trying to do is actually reduce that silence gap. So one of the things that we've been thinking about is essentially using the response generation capability in AI systems today to actually try to guess what the user might want to say based on listening to the conversation, knowing what the person has said in the past, and then tailor essentially the equivalent of a chatbot to actually make it respond for the person, right? And clearly what we're trying to do is not build an Alexa that will replace the person, but allow the person to control that response generation system at a higher level. So now imagine, someone asks a question, how are you doing today? And then you could imagine, the system generating multiple responses and the user selecting one of them, or maybe the user selecting a specific keyword that then the system generates a response from. And that tends to be a really complex problem because of the fact that now you have response generation systems that are trained on tons and tons of data, and you're trying to actually tailor it based on very small amount of data from the specific user to actually personalize it. And it needs to learn from extremely limited data because people with disability are not going to be generating tons and tons of data, right? So by definition, there's very small data that you're trying to nudge a response generation system to go do. And that's kind of a complex problem, but if you're able to solve that, then you really end up creating a much better system that can enable someone to respond in the moment rather than take a long silence before they can respond. So essentially, a lot of what I've talked about here is bringing these AI systems to help support users in these different settings and many more. And ultimately, to be able to do that, there's a set of capabilities that requires that robust perception and action in the real world, right? We talked about being able to understand what action the person is doing, being able to create a response in the moment, being able to understand the intent of the user, and then generate the right dialogue based on that intent, being able to observe the whole scene and understand the activities along with everything else that's going on before it actually can generate a response, or even understand the emotion of the user and help support the user in that. So essentially, you can think of these, while it's really hard to go and build all of these things for every single experience, there is a common set of capabilities where if you're able to do that robust perception in the real world, you could really expedite having these AI systems that can actually support users in these different settings. And there's a lot of similarity in these different settings. So let me talk about a few examples when I talk about robust perception in the real world. So, I talked about this notion of understanding what activities the kids are doing, for example, or what actions people are taking in manufacturing setting. So there, when you think about it, right, there are multimodal signals that a system can actually use to try to understand what activity is performed or what action is performed. There's what you could see in the camera. There are all the different poses that someone have. When the kids are, for example, jumping up and down, and we're trying to create an experience that's based on a lot of activity to make them much more active as they learn, then we need to really understand their posture. Are they jumping? Are they moving? Are they pointing? Things like that. There's also just kind of the scene in more generally, and trying to understand that they just put these tens and ones together correctly, and or what specific action and what device did this person use, and so on. You could also think about audio as a main piece of that puzzle, right? I mean, sometimes you can actually identify as people what's happening in the background, even if we can't see it, just based on the audio in that environment. There are a lot of other signals, like, for example, being able to use RFID as a way to actually bring in what type of tools people were using to perform these type of actions. So if you put all of these different signals together, you want to really essentially create a multimodal activity recognition system that's able to take inputs from all of these different streams and then come up with a much more robust activity recognition result based on that. And as you fuse these signals together, you can start to essentially choose to give more weight to one signal versus another based on the uncertainty in the result of each one of those streams. And then you could actually fuse these signals differently. On the multimodal natural interaction system that I just talked about, right? We talked about the notion of being able to actually listen to the conversation. So there's clearly the audio input as a way to try to understand what intents the user have. You could see what they're doing, the pose, are they shaking their heads? Are they nodding in agreement? What facial expressions do you have? Are they totally confused, right? Do I want to repeat as a tutor the thing again because the child just didn't get what I said and they didn't say anything? They just stood there and they looked that they are confused, or they're, from their tone of voice, they seem to be stressed out, or they're unhappy about what's happening, or they're very excited and maybe they want to do this game again. So you take all of these different inputs as you're building this dialogue management system, and trying to extract the intent and the state, and then as a result, generate the appropriate response. I mentioned a little bit about emotion recognition. And in fact, if you think about it, emotion tends to be a fantastic input, right? Because not only does it give a sense of the context of the user, are they excited, are they learning, are they confused, but it also gives a really nice feedback signal to the AI system, because if you're actually getting frustrated with what the AI system is generating for you, then you could actually use emotion as an input to that system to continue to improve it. It's kind of like an implicit signal, just like as humans, we learn from the emotions of people around us. So if you think about that, it's a very hard problem to solve, right? Emotion recognition is, I always joke that it's probably something that would take forever to actually get right. But what's interesting about it is that as you bring in these different signals, right? Signals from the voice of the user, signals from the facial expression, signal from what has been said, signals from the physiological data like heart rate and things like that, you could put all of these together to start to bring a more capable AI system that can actually be more accurate, because it's able to get input from all of these different signals. And as a result, the fusion of all of those ends up being more accurate. So, I kind of talked about all of these different robust perception capabilities and what is needed to actually build these type of experiences. One of the things that I would say is, which we sometimes don't pay a lot of attention to, is that all of these AI systems will always have a level of uncertainty and inaccuracy associated with them. And we can't really wait until the AI systems just become highly accurate, right? And so we have to assume that there will always be uncertainty and inaccuracy in these systems. And despite that, be able to use that. But to be able to use that effectively, we need to be designing these experiences with that uncertainty in mind. So as we think about a human AI collaborative system, you use the uncertainty as an input in the design of that experience to say, okay, well, here the AI system really has no idea what it's doing, or it's not really sure about what it's doing. So let me rely more on the human actor here and bring the human into the loop to help close that loop. And, we know that, depending on how you would design that AI system, that sometimes AI systems will spit out results for you. A machine learning model will spit out a result irrespective of whether it's accurate or not. So one of the areas that we've been looking at is how do you start to use probabilistic computing and Bayesian deep learning as an example to bring the level of confidence in the decisions that were made by the system along with the decision, which tends to be much more accurate than simply what you would see as the softmax output, for example, of a model, right? So as you use a Bayesian deep learning system or model, then what you end up getting out of that is actually a more confident measure of that certainty of that decision. And what you see here in those graphs that I'm showing is that, in the first system where you're actually just using the softmax, you'll see that the system is spitting out, for a similar level of accuracy, confidence, even when it's actually giving a decision that's totally out of distribution from the data that the system was trained on. But if you look at, for example, the Bayesian deep learning system, you could actually see it giving higher confidence in actually the data that's in the inferences that are based on the in-distribution data, and it's showing lower accuracy or confidence in the in doing inferences of the data that's actually out of distribution. And this is really what you want, right? You want the system not to just spit out an answer, but to spit out an answer along with what its certainty level in that answer. And then the designer of that system can utilize that uncertainty in a way that can make the complete system more accurate, because it's, for example, bringing in the human actor when it needs to. So, a lot of what I talked about in many ways has, a lot of advantages by bringing in humans and AI together and help support humans and amplify their potential. However, as I said, there are a lot of other concerns that start to creep up, right? I mean, as you start to collect all of this data about humans, then privacy clearly is something that we need to be paying attention to, both in terms of what are we capturing and making sure that we're reducing the difference between what we're capturing and what the system absolutely needs to do the inference that's required, but also where do we share the data, right? Who are we sharing the data with? Are we pushing the data collection all the way to the edge of the network so that we can only do the inference at the edge and then throw away all of the raw data, right? If we don't need to see the actual data that's coming out of a camera, then we should just be doing the inference and understanding the action and not having any raw data. Or if we're able to understand the activity, not from a camera, but possibly from a wireless sensor, for example, where we don't even see the output that's being captured out of a camera, then that becomes, in some sense, more privacy preserving and more privacy supporting. Another aspect of this problem is transparency, right? If we bring in human and AI together to perform these tasks, these systems need to be very transparent. People need to understand what these systems are doing and how they work and figure out how to actually, why they made the decisions that they've made, and be able to interrogate that, but also be able to correct that, right? In cases where there are inaccurate decisions that are being made, then the human can actually intervene and correct that outcome and say, this is not correct, and this is what I would like the system to actually be able to do. So the human has to have a reasonable understanding of how the system is actually operating, not just a black box. Also bias, right? So as we know today, as we use AI more and more to make all sorts of decisions, many of these AI systems are trained on data that's already biased. So we need to be able, as we develop these systems, to look for these biases, right? Is the system gender biased, for example? Is it providing different outcomes for people with specific race or ethnicity or whatever? And we've seen a lot of different examples where AI systems are actually completely biased in the way that they make their decisions, because that's the type of data that they were being trained on. But ultimately, if we step back and say, where do we want these AI systems to go, right? We need to, as developers of these AI systems, we need to make sure that we're developing these systems responsibly, that we're making sure that these systems actually work in the way that they're supposed to work, that it's preserving people's privacy and expectations of what these systems are doing, and that they're not actually biased in the way that they perform their actions. So for us to be able to actually bring about these better outcomes with humans and AI, collaborating and making sure that we're not marginalizing people, but actually help support and amplify their potential, we really need to be thinking about, from the get-go, developing AI responsibly. So with that, I thank you very much, and I look forward to answering any questions that you have. Thank you very much.
So now this section open up for questions. So if you have questions, please type in the Zoom chat window. I'm going to kick off the question section. Lama, are you here? Great. So I think thanks a lot for this exciting talk. I think this is a very exciting and interesting area. So what you mentioned some of the challenges. So what do you see in this topic of amplifying human potential with AI? So what are the key challenges now? Thank you.
I mean, there are a lot of challenges. I mean, as I kind of tried to get into, building systems that can understand and communicate with humans is really very hard, especially that humans are in many ways, hard to predict. Doing that in settings that, are more natural, that are not controlled experiments, that can be in different types of settings, tends to be quite problematic for AI systems. But also a lot of the stuff that I ended with around uncertainty in decisions that happen, and people not having an ability to sometimes even understand or have transparency in these systems that are actually trying to perform that action with them or help them. Those are all, in many ways, unsolved problems, really, right? I mean, we're still trying to kind of address it, and we address it incrementally in different ways, but those are really hard challenges that really require a lot of exploration and much further research.
Thank you. So next, if you have question, again, you can either type your question or raise your hand. So we can unmute you so you can speak your question.
By the way, are you able to hear me well? Because I'm having some issues with my network, but I'm not sure if I'm coming through.
Yes, we can hear you well.
Okay.
Yeah,
Great.
really appreciate your effort. So Rama, she actually is traveling, but make different effort to make this happen. So while we are waiting, one more question I have is you mentioned the privacy at the end of your talk. So with your experience, so what's your envision of the role of edge and cloud in future system of human and AI collaboration?
Yeah, great question. So, I mean, I would say kind of if you think about the privacy problem, it kind of breaks into a few different parts, right? One is you want to make sure that you're only capturing data that is needed to perform the inference that is needed, right? So let me give you an example. So let's say you're trying to, let's say that the use case that we're talking about is helping elderly people stay in their homes longer, right? So aging in place. So there, one of the things that people care about is making sure that they are doing their normal actions, right? They're going the activity of daily living. They're going to the bathroom. They're going to the kitchen. They're cooking something. They're having a conversation. Whatever. Sleeping, waking up, doing all the normal things at home. Now, one of the things that we know is that people are motivated to stay in their homes longer, but they don't feel comfortable with like cameras being all over their home, taking videos of them. So when I talk about the notion of reducing the gap between what is captured and what's inferred, you can think about, so one of the areas we've been looking at is Wi-Fi sensing, right? So you could think of actually measuring people's activities using Wi-Fi signals, and the disruption that they cause in the Wi-Fi signals can be actually translated to infer motion in these different places. Now, it's a much less accurate sensor. You're not actually seeing a picture of somebody, but you can infer activity. And there you're actually kind of reducing that gap between what's sensed and what's inferred. Now, the second piece of the puzzle, which is, I think, what you speak to, which is if you, let's say you need to use a camera, right? But you need to use that camera to infer, I don't know, somebody's heart rate out of the camera or something like that, right? Where you actually need that camera signal. Then if what you're trying to do is just do that activity inference or health inference or whatever, then if you do that right where the sensing is happening, and then you drop, right, you just feed that into the inference and you drop all of the raw data that you captured, then by pushing that compute much closer to the edge of where the actual capture is happening, you're reducing again the possibility what shouldn't be captured. Then there are a lot of other parts about, how do you control access, who gets access to what, how do people even understand what's being captured? Because if you have a camera and the only thing you're getting out of it is a signal that says, here's somebody's heart rate or here's their activity, you have to be able to actually show them that that's what comes out of the system, so that they're also not concerned about, okay, well, there's a camera, is it actually capturing me, in these weird settings or whatever. So all of these things, end up in some sense much easier as you push computation to the edge.
Thank you, Rama, for sharing your vision. So next, so we open up for questions. This is a great time to directly interact with Rama. So if you have questions, please type your question or unmute, raise your hand so that we can unmute you.
You actually asked the two typical questions that I always get whenever I present any work that has to do with human AI.
I think this is exciting.
Everyone is concerned about privacy.
Yeah, I think this is an exciting part. I think although AI has achieved a lot of progress, but in the end, people are most excited about how they're gonna enter our daily life. So your topic and your team are really working on that. So, but I do envision we're still facing a lot of challenges. You probably have deep understanding what are those key challenges. I think also Edge and Cloud is a debating. So it's great to hear your insights. So so we have 3 more minutes for questions. One more question I have is in the different area you cover. So based on your experience, so which are more closer to be used in practical setting? Meaning I know different area, those different application, probably the challenges are might different. So based on the progress in your team, in the community, which you envision will be practically used sooner? Yeah, thank you.
That's a good question. I mean, I think it's a question of which ones, because I think there's kind of a long-term vision of how far you can go, and then what are the incremental steps to get there. And a lot of times it's a question of not just the complexity of the task, but the investment and the return on investment, right? So that's why I think if you look at manufacturing, and even if you just kind of think about even the proliferation of things like robotics, and I would argue that robotics also is moving in this direction, which is how do you do human robot collaboration, right? Not just I would imagine that manufacturing specifically ends up being, a place where both investment and the possibility of where AI can come in and help is probably ahead. The problem with people with disabilities and that space of assistive computing is that funding typically tends to be quite low in that space. And because these solutions tend to be so specialized for a very specific disability and doesn't leverage the economies of scale, you see less investment and less funding in those places. However, if I just talk about the complexity of the problem, I would say, I think anything that has to do with children and trying to bring AI systems to work and understand children. I mean, just think about something as simple as speech recognition, right? I mean, we know how well speech recognition today works because of all of deep learning and innovation in deep learning, but it really doesn't work as well at all on kids, right? Because it's harder to get kids data, all of that. If you try to talk about natural interaction with these systems and collaborating, it's much easier for us as adults to actually, communicate with an Alexa and change the way that we communicate so Alexa can understand us, right? But you don't see kids doing the same thing. So in some sense, like I would say from a complexity of the problem, I think education might, be up there. In terms of the funding of the problem, I would say assistive computing tends to be the one that's least funded.
Thank you. Thank you for sharing your thoughts. So one question from the audience is Xiao Hu. So I'm gonna read his question. So it's great to hear your introduction. My question is that what specific methods do you advise or apply to protect the privacy of the input from the input side? For example, the client in the inference process.
Yeah, so I mean, maybe let me capture what I was trying to get at. I would say one, in the design of the system, make sure that you use the most privacy preserving sensor that can be used to detect a certain outcome, to infer the outcome. So that's what I call reducing the gap between the sensing modality and the inference. So that's number one. You need to ensure that the user is capable of controlling where that data needs to go and who can it be shared with in a way that is accessible. Because if we're talking about elderly people in their homes, right? I mean, we need to make sure understandable and so simple and so directly, controllable by the end user to make sure that people have control over that data and where it goes. Third, I would say you want to try to ensure that no other data is captured outside of what is inferred. So if people agree to a specific inference that's coming out of the data, if I am, as an elderly person, say, it's okay to capture my activity, I just don't want my video to be captured, then you need to make sure that you're pushing that compute next to the sensing so that sense data is not actually being sent out to actually do the inference, for example, in the back end. And if you need to do it in the back end, you need to ensure that that pipe is totally secure and nothing is leaking from where you've captured it to where you've inferred it and dropped it. So those, I would say, to me, are kind of like the most obvious places where, we could actually make a difference. And ultimately, what I talked about earlier about transparency, people need to understand what the system is capturing about them, right?
Yeah, thank you for your answer. So to stay in schedule, we have to stop here, but I believe if you have further questions, Rama will be happy to address offline. And let's thank Rama again very much for this a great talk and very exciting area. And thank you all for attending. We will have a break and then we will have the next paper section. Yeah. Thank you very much.
Thanks for having me.